Our next talk will be with Dr. Ahmed Hassan. He is the Canada Research Chair in Software Analytics at the School of Computing at Queen's University. And he will speak to us about the challenges for the industrial adoption of AIOps innovations. Welcome, Dr. Ahmed, and the floor is yours. So.
Okay, sorry. Can you hear me? Can you hear me?
Yeah, we hear you, but slides are not yet shared.
You can see them now?
Yeah, but not in slideshow mode. Yeah, it is.
Okay.
It is on a screen, but not
now?
in slideshow mode.
How about now?
I think you need to. Yeah, now perfect.
Now perfect. Okay. Oh. Sorry. Okay, you can hear it now. You can see it now, right?
Yeah, now perfect. The screen is
okay.
the slides
Okay.
or any screen. Yeah.
Okay. Okay, good. Okay, so first, thank you for inviting me, and I'm sorry, I would have actually loved to be in Egypt to present this, but yeah, unfortunately, due to timing, I couldn't be here this time. So thank you for inviting me. I would say, you know, this talk is, I would say, a continuation actually of the previous talk. So what we really want to talk about is how now these AIOps innovations are integrated and used on daily practice. So I'm going to talk about some of our challenges in doing that. So not just getting the research, but as well making sure that these innovations are used on a day-to-day practice inside big companies and what that involves beyond just the research and the key innovations. Okay. To give you an idea, kind of just tell you where Kingston is. So if you think of Canada, there's Ottawa, there is Montreal, and there's Toronto. So it's like a triangle. Kingston is exactly in the middle. So, you know, it's 2 hours away from every place. So it's, you know, I call it centrally isolated. So we're close enough from all the big cities in Canada, but far away enough that it's an interesting city in itself. And it's famous for what's called the Thousand Islands. So there's lots of islands. It's on the water. So it's a nice area. Please, you know, if you're ever in Canada, please, you know, do come and visit us. Okay. Now, in Kingston, so what my lab is called, it was called the Software Analysis and Intelligence Lab. And the idea here is looking at intelligence and automation throughout the lifetime of a software project. So all the way from the beginning of the project, all the way to actually when it's in production. And this is, you know, we've been looking at this area for, you know, over 20 plus years. And what we look at is we look at all the data that's produced either by developers when they're working on a project, or by users when they're looking at and using the project. So, for example, crash report, field logs. We call these historical repositories. We call these runtime repositories, okay? And then we call these code repositories, things like Stack Overflow, GitHub. And today, I'm really going to be talking more on this part, which are the runtime repositories. So, you know, a lot of this research has been adopted in industry, many companies in particular. Today, I'm going to talk about 2 examples of work that we did was Alibaba and it was BlackBerry. Okay, so particularly I'm going to talk today about AIOps, and Professor Peng already kind of explained this quite well. But the idea is there's a lot of information happening once the software system's in production. You know, how we can use that information to ensure that the system is running, you know, in a good state. And second, how do we make sure that that information can be fed into the next version of the software system when we're developing it? Okay, this is an area that's getting a lot of interest. As you have seen, Dr. Peng talked about a lot of research with industry on there. There's a big, you know, actually this event has been already delayed for 2 years because of the COVID, the pandemic. But yeah, so the idea here is to bring all these researchers and from industry and academia to talk about this topic. Now, the key point, so if there's any one slide you're going to be awake for, this is the one slide, okay? So this is the key message here I want to kind of emphasize is that it's not just sufficient to just bring in a very fancy machine learning model and, you know, demonstrate that it works in one state on one snapshot of the data, but how do we make sure that that innovation is of value and is used in a day-to-day setting in a company. And this comes down to this kind of 5 big things that we have discovered over the years. So first, it's very important to have the trust, because a lot of times the machine learning model is a black box, okay, or is using metrics that the operators don't trust or don't know about, even though it might perform better. They have a less tendency to actually use that model and use the system behind the model, you know, that's being driven by that model. So trustability is important. Interpretability is another key point too. So the idea is, if a system tells you there's a problem, it's not sufficient to know that there is a problem, but it's sufficient as well to be able to explain to the other people in the company why this is a problem and why you, for example, want to stop a release or why you want to reboot a service. Scalability is another issue too. So that's some of the challenges. Is a lot of these systems, you know, the window in which you need to give the warning is very limited. So if system, you know, might be using very sophisticated machine learning techniques, and it might take, you know, a few milliseconds, a few minutes, that is already too late, okay? And then the other thing is maintainability. So the idea here is well, the system works perfectly well with the academics in the room, and there's a lot of machine learning experts in the room. One of the problems is once the machine learning experts leave the room and the academics leave the room, the operator that's using the system on a day-to-day basis will actually have challenges on that. So how do we make sure that they can maintain it easily? And then finally, the systems and the research need to be evaluated in context. And that brings a lot of challenges, because traditionally, things like tenfold cross validation, you know, type of evaluations in machine learning literature is not really valid in this type of systems. And I will talk a little bit on that, okay? So, you know, so as I said, so I'm gonna talk about 2 examples, one of BlackBerry, one of Alibaba. So the idea here is you have a new release is coming and it's running, and you now have data, a lot of data from old release. Traditionally, what we do is we create some type of signature, and then that signature, we use it to analyze, you know, outliers, find any outliers in the system, okay? And then these outliers then now are shown to domain experts, and then he or she needs to take a decision whether the example is a problem. For example, in the case of Alibaba, the system was used, actually is currently used to detect any anomalies in their whole data center. So in their case, they want to find out, you know, ideally they want to find out up to 4 days ahead of time if one of their machines will crash. And then if they know that ahead of time, then they could actually react and take the machine out of service. So, you know, they want to find it 4 days ahead, maybe 4 days is ideal, even if they can find it, you know, a day ahead. Finding it a few minutes ahead, it's not really that useful to them, because you just don't, there's not enough time to react. So that's one. And second is when somebody flags that a machine has a problem, he or she needs to be able to explain why they believe it has a problem. So it's not sufficient to say that this black box deep learning model is saying there's a problem. You know, their manager needs to have a good understanding of why. And this is one of the key challenges. It's not just the performance of the model, but the interpretability of the model. Okay, so this is, you know, so this is the example of the Alibaba machine down alert system. So we take a lot of data. So we take alert data. We take data even about the location of the machine in the racks, because sometimes in the very big data centers, there are part of the racks, for example, the air conditioning is not coming to these parts. So the hard drives might be warmer. So if a machine dies, maybe the machine above it or below it might actually die as well, because, example, the hard drives are overheating on that, around that machine. We take as well the characteristics of the hardware itself. So all that information is fed in, you know, is sampled, you know, and then a machine learning model is trained with hyperparameters tuned for the machine model. Then after that, the model is evaluated, and then finally, you know, there's the results for which now the analysts can examine. And then more importantly, they want to be able to go back and analyze the results and understand why, you know, why the system, this machine learning model is warning about the machine is going to go down, for example. So really what comes down to is, you know, we have this DevOps cycle here. So we're developing the code, in which we're putting monitoring code. The system is now being deployed, and then during operation, the monitoring code is producing monitoring data. That monitoring data gives feedback into development. So there's 2 things here we need to get right. So first, we need to get the monitoring code right. And second, we need to get the monitoring data is used in the right way. This is the big challenges when it comes to AIOps. So first, making sure you have the right monitoring code in your project, and second, you have the monitoring data in the project. I'm not going to talk a lot about this today. I'm going to be talking more about the monitoring data used right. Okay, and then here's an example of many of the challenges. So here, how you do the logging, what places you need to do the logging are kind of things around the monitoring code used right. And then the monitoring data used right is all these things about failure diagnostics, analytics, and Professor Ping's talked a lot about the blue part here. He gave a lot of great example working with Alibaba and eBay and so on, and Microsoft. Okay, so not as much we're going to be talking today, but I want to give you a taste of some of the things. Is today when you want to do logging, so inserting log message in a piece of code, a couple of things that come up. Where do you log? At what level you log? What to log? Why to log? And when to update log? So if you don't answer these questions, then you'll end up, you could pretty much have for every line of code a logging statement. So that's one extreme. And the other extreme, you don't have any logging statements. So now the problem is when looking at large projects, developers tend to have a lot of challenges in actually putting the right logs. Okay, so what we have found, and other people have studied as well, is a lot of times is that developers either might change the logs. Keep in mind now, when these logs are changed, a lot of the AIOps techniques will actually break. Okay, so that's one of the problems, is because these AI techniques are using the logs to parse them. But the developers, when they're changing their code, are not aware of the AIOps tools that are analyzing a specific log line. He or she might think that nobody cares about that log statement, and that log statement is only used by them for debugging. Okay, so for example here, so one of the challenges here is when you change a log, when you change a piece of code, it's important as well to reflect that some of the changes in the logs, if the logs are impacted. So we've built a lot of models to give people suggestions on where they need to change their logs. The AUC is a metric that goes from 0.5 means we're random guessing to 1 being perfect guess. We're very 100% accurate when we give suggestions, and these models are very accurate in giving people recommendation on where they should change the logs when they do a code change. Okay. The other thing is the log level itself, right? So looking at a lot of open source projects, you'll find that a lot of times the developers there would be bugs filed saying, for example, the logging system is logging too much. Okay, so this comes down again to what level you need to be logging at. So whether you log at trace, debug, info, warn, error, and fatal. So these ones are very very rare. These ones are very frequently logging. So you need to figure out what's the best log level you need to do at. Today, there's not a lot of automated support for developers on this, and that's some of the work we've been working on with developers on that. Again, this is the AUC numbers on this. So now let's more talk about the monitoring data and the AIOps itself. So a couple of key points that happen is, first is you have a lot of complex, large, heterogeneous data sources, and Dr. Peng has touch on this, right? So you have logs, metric, traces, alerts, and they come in, in gigabytes and terabytes of data, sometimes per hour. Okay, the data as well is extremely balanced. So whereas traditional machine learning models deal, with say 10% of the case you want to predict or something like that. Here we're talking, for example, let's say in the Alibaba case, 0.01% of their machines might crash at any one time, right? So it's extremely small percentages, making it very hard to use the classical machine learning models. Okay. The second thing is when you do the machine learning evaluations that traditionally are used, things like tenfold cross validations don't make a lot of sense, because what ends up happening is when you do tenfold cross validation, what it does is you divide the data into 10 pieces. 10 chunks. You take, say, nine of the chunks you train on, and one of the chunks you test on. But now you lost the key point, which is the time aspect over time. So the data is going over time. It's a time-based data. So there's a lot of work that we've been looking at into basically time-based evaluation. That's one. The second thing, it's not sufficient to say that a machine will die in 6 months, or a machine will die, you know, in a minute. There's that sweet spot. So it's either you're too late or you're too early giving the predictions. Okay. So, and then another challenging aspect too is over time with very big data centers or very big installations, there's a lot of updates that are happening. Whether the machine, Windows gets updated, whether a specific library gets updated, and these updates, whether at the software level, even at the hardware level, will impact these signatures, these fingerprints that I talked about earlier. So it's important to have systems that are robust and that can deal with that. Okay, so let me talk about the BlackBerry setting. So a very simple example of this is, you know, so you have a metric, let's say that's your CPU, and for the last, you know, 6 months you've been collecting data on this project, and what you'll find here is that the dotted lines here, okay, are telling you pretty much the normal behavior range, okay, and then the black here says this is a day where everything, all the CPU was in the good range. And then whereas the red one here will tell you, you see here that in some moments during the day, it actually bypassed the upper limits. So that's a very simple example of an AIOps technique. And then ideally this needs to be flagged and analyzed, okay? So here examples of a good run, here's an example of, you know, a bad run where it was just all over the place. You had so many violations in there. Okay, another examples of that could be creating these pairings. So, you know, you acquire a lock, you release a lock, right? So in this case, you have these events, so E1, E2, E3, and E4, and they keep on repeating, and then one time you see an E6. So this is exactly the type of event that needs to be flagged. Okay, so this type of idea, you know, we have kind of looked at that maybe back a few, well, I guess maybe 15 years ago. We were looking at the Dell DVD store, and we were trying to understand how Dell tests their data centers and their servers, and looking at their data, and we were able to build this pairing model. So example, in this case, it says, when this event happens, okay, when this event happens, 98% of the time, this other event follows it. But then less than 1% of the time, this other event follows it, and then even 358 times, this event follows it, okay? So now this pairing, if you look here, is actually sorted because we look at the statistical properties of these events, and this is flagged very high, 79. So this is what's called a Z-stats, and tells you how rare this is to happen. So then when a developer actually when an operator wants to flag this and send it to the developer, they can copy and paste this part of the table and flag to them the reason why they feel that this is extremely rare situation and that needs to be investigated, okay? So, you know, this leads to a huge reduction on the logs, and the precision is around 100% to, you know, around 50, 60%, okay? Other ways too is, you know, looking at not only the pairing, but as well as looking at the timing, okay? So here is, you know, it looks at a sequence. So same like the sequence said, it's on E1, E2, E3, E4. And then it looks at how much deviation is happening between these different things. So in this case, you can see that throughout the 2 days, the same amount of event happened, but however, it has this deviation. So then an analyst can click on that, okay? And then they can see this type of analysis here. So what that analysis says is for this sequencing, this E1, E2, E3, E4, this flow, okay? You know, last day, this is how it looked, this is how much time it took for that. So this is a distribution of every time this event happens. One time it took less than, you know, half a millisecond, sometimes it took 1.5 millisecond. And then in the new day, this is what it looks like. And you can see here that there's an increase in the distribution over time, okay, in the average of the distribution. And this is looking at it over time too, because sometimes due to caching changes in the logic, you might see this, for example, at the beginning of a run, and then later on, you know, later in the day, this adjusts. And you can see this is happening consistently. This is actually was a bug in MySQL, the open source database that was discovered and reported by us many years ago. Okay, so now what happens is I've only looked at the events, but now as an analyst, I want to even figure out what exactly caused this. So I can click on this sequencing here, the events, and then I can actually get a table that says, look, this is the sequencing, and this is how long it usually takes between this event and this event. It takes 1 millisecond in the last day, but now it's taking 1.1. But then now I can see that between event 2 and event 3, it takes 0.5 in the past, but now it's taking 1.8. So that's why this is how this number here, the sorting is happening. And again, because this is a very simple log example, it's very explainable, and the analyst could just copy and paste this, and it's easy to have these discussions because it's very fact-based instead of just being only on the machine learning model giving a recommendation. Yeah. Other problems I explained, so this other challenge is the heterogeneity. So different labs over the years might change, different machines might get upgraded, different either the hardware, the operating system, the machines themselves. And now how do you make sure that a signature that's created here applies over here? So here's an example of some of the work we have looked at is instead of looking, whereas in the past we showed you we look at the metrics, the number, okay? Here now we convert the numbers to ranges and we go medium, low, and large, okay, and high. And by using that, we can actually create relations that are stable over time. Because remember early on, I think it's not only sufficient to have a good performance model, but we need these models that can survive over the years as your data center or your hardware is being upgraded. Okay, so now if we see this, so usually when the database read rate is medium, and the throughput is medium, then the request queue size is low. But now when we see it high, then this is something that could be flagged and analyzed, okay? So this is an example of kind of showing this happening here, and then here it's kind of high, and then somebody could actually look at it and analyze it. The beauty of this is, even if you were to upgrade the machines, the speed of the machines, you upgrade the network, whatever type of upgrades you do, because the relations are creating between the data that's being learned, we have removed the timing, the exact numbers, is considerably more robust, okay? Which means that the machine learning models that are trained can survive over many years. This has been tested on, data could be several years, in the past, and still you could use the old data even on new hardware. Okay. So again, so this is it shows you an example of this. So here is, this says, okay, there's a performance regression in the CPU utilization. You can click on the rule. It will actually show you the rule here. So it shows, okay, this is the rule. This is the numbers we expect. So we expect this to be at medium, this to be a medium. However, we see high. These two are high. So the CPU utilization and the memory utilizations are high. And then you can actually click on this little graph here. When you click on this graph, it actually shows you for these metrics, kind of where in the lifetime or during the day these violations are happening as well. Okay. Other challenges as well as looking at memory leaks. Memory leaks are much more challenging than any of the other metrics we discussed because when you see there's a memory leak, you see a big rise in the memory. What ends up happening is the reason the leak happened could be, half an hour or an hour ago. So how do you create a metric? How do you create the signatures that are actually capturing the delay, right? So this is one of the challenges we kind of have been addressing as well, the delay in the impact of an event happening. So somebody allocating memory and then the leak happens, an hour later. Well, the leak has happened, after you allocate the memory, but you're really seeing its impact on the memory increase over time, over, an hour or so later. Okay. Now for the Alibaba case, so what are the challenges that they had is they already had a system. The system was based on a lot of kind of hints on some metrics that they have developed. Okay. And these metrics that they have developed are able to tell them, okay, there is clearly a distribution between those that are likely to fail on the left and those that don't fail. Now, the classical way to approach this, or at least the common way in academia, would be to just take this, bring in a deep learning model, use the raw metrics instead of the metrics that are developed by the experts. And then now the model might perform better. Unfortunately, once you do that, now there's a whole trust situation you need to deal with, because they need to relearn the system and whether they trust the metrics that are being developed by the machine learner, okay, the deep learner, okay? And second, whether they trust actually the deep learner's performance as well. Because remember, a lot of these, any model, any machine learning model has, you know, say a 0.9 accuracy. What happens if you're the 0.1 where it's not accurate? So one of the things is so we worked on them with trying, instead of starting from raw metrics, starting from these metrics that they have developed over the years, because they trust these metrics, okay? So, and then instead of building the metrics using a deep learner, we actually worked on creating metrics that made sense for them. So interviewing them and working with them on some of the metrics, trying to gather their intuition. So in this case here, you know, you start from this is the raw metrics alerts data, but now we can convert that to temporal features. So things about the frequency and the ratio of the alert data. So this is the raw data. This is the metrics that are derived. So this point here is the importance of feature engineering. Today with deep learning, the idea is that, you know, the deep learners can do the feature engineering for you, and it is true that it can do it. But then now these new features are very hard for the domain expert to really get a sense of what they do. And second, it's very hard for them to trust them because they don't know where they kind of came from, okay? So yeah, so, you know, so from one data point, we can generate all these metrics here. So that's, you know, the key points here. The other thing is the data skewness. Remember we talked about that, you know, 0.01% of the machines in a data center could actually crash, which means that you have very little data to actually learn from. So the other thing is, another emphasis here is how do you increase these negative samples? So if you have 10 million positive samples and you only have one negative sample, it's very hard to build learners using these. So here again, we work on oversampling, but whereas traditionally the oversampling would be done using synthetic techniques, again, working with the domain experts, we developed oversampling techniques that capture their intuition. So the point, for example, in their case is like, whether, you know, so if you have one data point which something happened bad, so the machine crashed, okay, now you can collect hundreds of samples before that event occurred, and now you can have 100 negative samples instead of only having one single sample, which is the negative sample. Because once the machine dies, you know, moving forward, you could still consider that the death of a machine at minute 1 implies as well that the machine is still dead at minute 2. And that type of intuition, working with domain experts, is essential to make sure that you can deal with data skewness using, you know, the domain expert knowledge instead of only just the machine learning theoretical knowledge. Okay. The last thing is what I talked about. So this is the in-context evaluation. So when you look at cross-validation, as I said, you divide the data into pieces. You take one of the pieces for testing, and then you leave the other pieces for training. But as you can see here, in this case here, I'm training. So this is over time. I'm training here on the white stuff here, but I'm testing on the black stuff. And as you can see here, this part here that I'm training on is in the future. So that doesn't make a lot of sense, okay? So instead here, two things that we have done. First is the idea that we want to make sure we actually train, you know, make sure the time dependencies between the data is valid. And second, because, and especially in their case, they said, you know, if you give us a warning, you know, up to 3 days ahead of time, that is not sufficient for us to actually start the process to, you know, change the machines. So that data here is actually dropped from the learning. And that because there is some, you know, and in this case, it's 72 hours, it could be 3 hours, whatever the domain expert needs for them to react for your warning. So, because it really doesn't make sense, you know, if we learn something here and we say the machine is going to crash in 3 minutes or 60 seconds, right? So it's important to remove that and to evaluate the models with that in mind, that there is a lag between when the model gives a recommendation between somebody needs to react to that recommendation. Okay, so that's what we call evaluated in context. So with that in mind, we took this approach, okay, and we compared that to what's called so this is a deep learning model, so LSTM, okay. This is a Mingo. This is an approach that it was done by Microsoft Asia, okay. And then this is our approach here. So our approach here uses a random forest, a very basic machine learning model compared to very complex machine learning models, whether it's LCM or Ming. And you can see here that it actually performs much better. So on the right side here, this is when we do the oversampling, and this is the gapping. This is where we leave a part of the data out to reflect the fact that when somebody gives a warning, there's a reaction time, and that reaction time needs to be considered in the evaluating of your performance, okay? The other thing that's very important here too is the random forest techniques here. So you can see the speed of the training and the speed of the testing. So here where we're talking, hours or minutes, here we're talking seconds. So exactly in 2 seconds, the random forest technique can actually give its recommendation or its predictions, okay? This is a lot more time, is wasted by the more complex techniques. Okay. And then the last thing is, is understanding. So again, because of the random forest model is a simpler model, we're able to open the random forest model and look at the features and look at the features of driving that. And based on that, they could put additional telemetry in their data center to capture even closer the different features that are more impactful here. Okay? And be able as well to understand why the model is giving them these recommendations. And it's very important for them to understand, not just only for themselves, but it's really hard to go to your boss or go to the data center management team and say, we need to take these 5 machines down. And when you ask why, you say, because this black box deep learning model has given me a recommendation. Whereas in this case, they're able to demonstrate why, they're able to explain the rationale for what's happening. And they're able as well to have a time. Remember that 72-hour window for them to actually give the recommendation to react. Because that involves, it's not only when you see a problem in a machine, you could just run and do it. There's a whole process inside of a company. And even if, even the process, even if you have the machine sitting on the rack beside you, just reconfiguring the machine and moving all the client virtual machines that are running on it takes some time to happen. Okay. So the other things now moving forward, we've been looking at this whole AIOps area and looking at really these kind of couple of key areas here. So A is, and I give you an example of that. So, whether the models, the way they're built and evaluated, are there any data leakage issues, right? Are they learning from data in the future to predict things in the past? Okay? The other thing is how easy is the model to evolve over time? And then how do you interpret the model? So it is important, as I highlighted, is to make sure that the models are interpretable, explainable, such that the domain experts can defend the decision of the model. Okay. So with that in mind, this is my key points today. So first is, I talked about a lot of the area of research that we've been doing in the past few years on looking at software data, whether it's production data or development data, or even things like GitHub, right? We work with Professor Mohammed Al-Ramli from the University of Cairo as well. I work with him on some of these areas. And so, I'm happy to have discussions, if anybody's interested in this, either for him or please reach out to me. Okay. And, in particular today, I only talked about production data and AIOps. And I wanted to emphasize the importance of building models that the domain expert can trust, models that they can explain and defend, models that are scalable and that are maintainable, that don't require to have a machine learning experts in-house with you all the time. Right? And we're seeing this is happening. So just, if you know, recently Facebook had a full reorg of their organization, and they're putting the machine learning teams much closer to the production teams. And some of the reasons is because these models require a lot of maintainability and a lot of tweaking over time. So it's important moving forward that these models are kind of hands-free maintenance, low level, low cost maintenance. And then finally, we talked about making sure that the evaluations are realistic. So not learning from data in the future, making sure that the reaction time that's needed to actually deal with the recommendation of a model is considered when you're evaluating a model. I briefly talked about the research, AIOps, talked about some of the challenges around putting the right logs and then actually analyzing the logs correctly. We talked about common challenges due to the size of the data, due to the rareness or the skewness of the data. And then finally, I talked briefly about some of the key challenges that is across the whole area around how to build the right models, how to actually make sure that you evaluated them correctly and efficient and accurately. And then finally, whether the models are easy to interpret. So yeah, so is that it? Happy to take any questions. And thank you for inviting me. Thanks.
Thank you very much, Dr. Ahmed, for this wonderful presentation. Actually, I think many recommendations can be applied to other AI applications, not only AIOps. And the floor is now open to receive any questions. Okay, no questions here, but I think people also attending online and they may send some questions on the platform. So I appreciate if you check the platform for any, there is a question here sent online. Is it fair to say that when outcome of machine learning model needs to be explained or interpreted, deep learning is not the perfect model for that?
So I guess there's two answers. So first is it's important to consider the simple models first, okay? And then if the simple model is not performing well, then you can go to more complex models. So that's one. The second point is there is work today in deep learning, trying to build models that are interpretable, okay? However, keep in mind that sometimes the deep learning is used for two things. First is used for feature engineering, so you don't even know what the features are, and it creates features, and then now it learns from these features. So the interpretation part is still a bit challenging for deep learning, but there is work in the area to get there, but it's still considerably further than say 20 or 30, well, 40 years of interpretation, something like a random forest.
Yeah, okay. Are there any online questions? Yeah, we have some also while another question saying while in creative artistic works, when we are most concerned with outcome, DL outperform other models.
So can you repeat that one? Can you just repeat that one? I didn't understand. Oh, sorry. When in creating artistic works, when are we most concerned with them? Okay, yeah. So that's an interesting point, right? So when it comes to like generating of pictures or essays, like there's a lot of work on generating of text and stuff like that, right? And deep learning is very good at that. Now, the problem is when it comes to this type of work, the output is the final problem, right? So, for example, today, if your deep learner generates an email, that's it. That's the end of the email. But when your deep learner generates a piece of code, that piece of code is the beginning of the life of this piece of code. So that piece of code now needs to be maintained and changed over time, and you need to deal with a lot of problems around it. As you can see, there's a lot of recent studies that show, for example, that a lot of the source code generation techniques end up generating code that has a lot of vulnerabilities in it. And so that's the big challenge here is, yes, it does perform well But the question is now, once you have this final output, what do you do with it? It's something that has not been considered as much in the deep learning field at this moment. But it's something that I'm expecting our colleagues in the machine learning to look into it more deeper.
Yeah, okay. Thank you very much, Dr. Ahmed, for joining us and for this wonderful talk. And now it's time to our break. We will come back to continue our agenda at 12:30. So enjoy your break.
Okay, thank you.
Yeah, thank you very much.